So today we are going to discuss about relativistic electrodynamics. So we know that the principle of relativity says that the laws of physics are applicable in all inertial reference frames. So what do you mean by an inertial reference frame? So we can consider two frames which are either at rest or moving with a constant velocity. We can name it as inertial frames. But in physics, there are so many other kinds of reference systems. For example, an accelerating system, which is not an inertial system. So Einstein, in his special theory of relativity, predicted the two postulates of the special theory of relativity are: first one is the principle of relativity, which says that the laws of physics are applicable, equally applicable, or the laws of physics are same in all inertial frames of reference. The second one is the universal speed of light. The speed of light is same, or the speed of light in vacuum is the same for all inertial observers. So actually, Einstein formulated the special theory of relativity, and the relativistic mechanics began at the time of Galileo event. So what will happen if something is moving in the speed of light? So let me pose a question for you. Is the relativity applicable to electrodynamics? So in electrodynamics, we have learned so many things like there is Coulomb's law, whether Coulomb's law is affected by the relativity, whether Biot-Savart's law is affected by relativity, or say we have different Maxwell's equations. Are they affected by principle of relativity? So in a first answer, we may say no, but if we have a deep thought, we will say yes, because let me pose an example to you. Consider a charge moving in an electric train. So we know that a moving charge can make and constitute a magnetic field. So we are standing in a railway station, for example, and the train is passing nearby. So the charge is kept inside a compartment of a train. So for an observer on the ground or on the station, the charge is moving with high velocity, and he will experience magnetic field, provided all other conditions are applicable. So consider a different situation where a passenger who is sitting in the same compartment along with the charge is measuring the magnetic field. For him, the charge is not moving because he and the charge are moving with the same velocity, or they are, for him, the charge is at rest. So for a for a particular situation where the charge is moving in a train compartment, for two different observers, the phenomenon is completely different. For one person, there is magnetic field. For other person, there is no magnetic field. So here comes the relativity, or even simply we can realize that the Lorentz force law, which says that the force is equal to force in an electromagnetic field is equal to QE plus V cross B. There is a V velocity term, so we can see the velocity term in different situations. In electromagnetic waves, in conduct, in radiation fields, or in Poynting vector. So in so many areas, we see the contribution of velocity, and we can conclude that the principle of relativity will apply to electrodynamics. In what extent, we will learn in the few chapters. Okay, so this is the brief overview of our first part of this chapter. So we'll begin with the Galileo's velocity addition rule. This is very simple rule. So consider a train which is moving at a velocity say 60 kilometer per hour, and a person is walking from the back end to the front end of the train with a velocity 5 kilometer per hour. So naturally, we'll conclude that the velocity of the person moving in the train with respect to the ground. So for an observer on the ground, the train is moving at a velocity of 60 km per hour. plus that person is moving at a velocity of 5 kilometer per hour. So effectively, for a person on the ground, he will see that the person is walking in the train with a velocity of 60 plus 5 is equal to 65 kilometer per hour. So generally, consider particle A moving with some speed with respect to ground C. So let the velocity of A with respect to ground or C be VAC. If another object B moves with some speed VBC with respect to the ground, then the speed of A related to BVAB, then VAC is equal to VAB plus VBC. So we can understand it clearly with the example I have cited. So one special case, if A is a light signal, its relative speed to B as well as C is the speed of light C. That is VAC is equal to VAB is equal to C. So consider the case here. VAC is equal to, that means if we put back those things in the equation 1, we will get velocity C is equal to velocity C plus VBC. So here the Galileo's velocity rules fails. When when an object is moving in the speed of light, Galileo's velocity addition rule fails. So how it was fixed? We'll see. So Einstein fixed this velocity addition rule with a simple correction. See the Einstein's velocity addition rule. If we forget the denominator part, it is the Galileo's velocity addition rule. VAC is equal to VAB plus VBC divided by 1 plus VAB VBC by C square. So if in ordinary speed, where VAB and VBC are very, very less than C, what will happen? 1 by C square will be comparatively very low and it can be neglected. So the denominator will become equal to 1 and VAC is equal to VAB plus VBC. That is the Galileo's addition rule in normal speed. But if VAB is equal to C, what will happen? VAC becomes equal to C plus VBC divided by 1 plus C into VBC by C square. So again, the denominator term will vanish and this will approximate to C plus VBC is uh, so C plus VBC will cancel out and you will get a C, because if we take the if we cross multiply the denominator term, we will take a C in the denominator of C VBC by C square and we'll get C into C plus VBC by C plus VBC, and that will cancel and we will get it as C. So if something is moving in the velocity of light, then say from the Einstein's velocity addition rule, even the end result, the compiled velocity will also be C. So nothing can move beyond the velocity of light. So that is proved by the velocities addition rule. So now we are moving to a different situation where relativity of simultaneity. So geometry of relativity. We'll call these 2 or 3 discussions as a geometry of relativity. Where the first discussion we'll start with is the relativity of simultaneity. So we imagine a freight car or just a compartment of a train or something like that, moving at a constant speed along a straight track. So we have a light bulb which hangs at the center of the car. Uh, so light travels in all directions at speed v. So we have a car which is moving in the velocity. So we have a freight car and we have a bulb at the center, and the light moves in all directions. So we are considering 2 directions, A and B. So consider another situation where the freight car is moving. So what happens? The bulb will move. So and the light was at a previous position, and we can see in the figure, the second figure. So the freight car is moving to the right. So the dotted lines indicates the previous position. So what happens now? The freight car is moving forward. The back end has reached near to the earlier position of the light. So the back end has moved near to the earlier position of the light, whereas the front end have moved farther away from the light. So we will not notice this thing in our ordinary life. If we move in a train or car, and if there is a bulb at the center, we will not notice this because we are moving at very ordinary speed, very low speed compared to the speed of light. So what happens even if we are moving, the light is having a higher speed, so light will reach us uh, far in very less time or no time compared to the time compared to the motion of the train. So in ordinary speed it is not applicable because we are moving in very ordinary speed or very low speed. But if the car is moving at very high speed compared to the speed of light, what will happen? So even before the light has reached the back end of the train, the back end has moved near to the light source. So we need so light needs some time to reach the back end. And if the freight car is moving at the speed of light, what will happen? The back end itself has moved near to the bulb, whereas the front end has moved away from the source of light before the time the light reached there. So, relativity of simultaneity, we consider two events, light reaching the front end and light reaching the rear end. So, in ordinary case, these two events occur simultaneously. At the same time, the light will reach the front end and the light will reach the rear end. So, for a stationary observer on the ground, these two events are not simultaneous. So, that is the case which I have discussed. The freight car is moving with high velocity. So, for an observer on the ground, what will happen? The light at a position it illuminates, and the back end moved near to the light, whereas the front end moved away from the light. So, for an observer on the ground, what will happen? The light has to travel more time to reach the front end, whereas it reaches the back end in less time. So for the light travels out from the bulb, the train itself moves forward. Thus the beam going to the back travels shorter distance than the beam moving to the front end. So according to this observer, who the observer on the ground, event B, that means light reaching the rear end, happens before event A. So for an observer who is not in the inertial system or who is not in the reference system, what will happen? He'll feel that as event which was simultaneous in one system is not simultaneous when he is observed from another system. So we'll conclude it like this. Events which are simultaneous in one inertial systems are not in general simultaneous in another systems. In another inertial systems. Okay. So we will now observe a different phenomenon called time dilation. So here we have a freight car and a light travels. A light is fitted at the top of the freight car and the light strikes the floor directly below. So for an observer on the train, if h is the height of the car, the time taken by the light to reach the floor is h by c. So that's so obvious. So the light is held at the top of the freight car and it moves straight down. If h is the distance, h by c is the time taken to reach the ground. So we have see not that I have showed the time as delta t bar. So wherever I have an overline or a bar symbol, it means that it is observed in the same system. So if something is observed in the same system, I'll put a bar or an overline symbol. Here delta t bar means it is observed in the same system. So in the same system, the light, the bulb reaches the floor in time h by c. So if the train is moving like a bullet train or not like a bullet train, even much higher speed, The train is moving like a light train. So for an observer on the ground, the train itself is moving itself with speed v. Here v is very close to the ordinary speed. The light train must travel further v delta t. So see the figure here. So the straight we have we are experimenting that the light has to reach the uh, point which is straight down the bulb. So we'll draw a perpendicular or straight line, and we assume that the light has to reach that exact point on the ground, which is at a straight line with the bulb. So what happens? The train has moved. So that point has moved further. That point has moved further by a distance v delta t. So that point itself has moved. The train has moved, and that point itself also moved. So the light has to travel an additional distance v delta t. So here, see, notice that I haven't put a delta t bar here because it is measured from another system. So here, instead of h, I have h root of h square plus v delta t the whole square. So, and I solved it. How do I solve it? I just took the, or I just took the square delta t square. What will I get? H square plus v delta t square by c square. So I just combine the terms with delta t square in one side and take the square root, and I got that delta t is equal to h by c root of 1 minus v square by c square. And we can notice that h by c is delta t bar. So delta t bar is equal to delta t into root of 1 minus v square by c square. So, so we'll again summarize it. Let delta t be the interval between two events. The events are light leaving the bulb and light reaching the floor. The time interval between two events are measured for two observers. Delta t measured on the train is shorter than that measured from the ground by a factor. Gamma is equal to 1 by root of 1 minus v square by c square. So we conclude that moving clocks run slow. Okay.